Let S equal 0, 1, union 1, 2, union 3, 4, and T equal 0, 1, 2, and 3. Then which of the following statements is or are true? There are infinitely many functions from S to T. There are infinitely many strictly increasing functions from S to T. The number of continuous functions from S to T is at most 120. Every continuous function from S to T is differentiable. Interesting. Okay, so I'm fairly sure that A is true. And let's write down quickly what these two sets are. Okay, so it's quite easy to see. I can construct pretty easily of an infinite number of different functions from S to T. Let's just say that every single number in here maps to 0 except an arbitrary number in this interval, and that arbitrary number will map to 1. Well, there's an infinite number of arbitrary reals in this interval. So that's an infinite number of functions right there that maps S to T. So A is correct. There are infinitely many strictly increasing functions from S to T. Strictly increasing. I suppose this is false. In fact, there are very few I don't think there are any strictly increasing functions, right? If I ignore this part of the set S and I restrict any function to the interval 0, 1, and I say that it's strictly increasing into the set 0, 1, 2, or 3, well, take any number between 0 and 1, call it x. If f of x is equal to 0, every value in this interval greater than x, you sort of instantly get broken. You instantly can't satisfy this condition. Okay, C. Option C is the number of continuous functions from S to T is at most 120. So I suppose here the important thing to look at is that if the function from S to T is continuous, then within this interval it has to be a constant. Within this interval it also has to be a constant, potentially a different one. And in this interval it has to be a constant, again, potentially a different one. So really, if it's continuous, we can kind of think of the set S as being only 3 points, right? The function has to be constant on each of these, so there's really only 3 possible inputs. And so the number of continuous functions from S to T, well, in the first interval, there are 4 possible values. In the second interval, there are 4 possible values. And in the third interval, there are 4 possible values. And this is 64, right? So there are, in fact, exactly 64 continuous functions from S to T. I think I did this correct. Right? In general, if you have a function, if you have the set of all functions, let's call this set Z. If Z is equal to the set of all functions from the set X to Y, then the cardinality of Z is equal to the cardinality of y to the power of the cardinality of x. And I mean, obviously the cardinality of s is infinity, but by restricting to continuous functions, we have to be constant on each of these intervals. So in some sense, there's only 3 points here. So the cardinality of this set should be 4 to the power of 3, which is exactly this. So I think that C is not correct. The number of continuous functions is 64. Why would they be trying to... I mean, I kind of think, given that this is sort of an exam type problem, I kind of feel like this 120 is supposed to be the result of some sort of... they're trying to... There's a trap here to fall into, but I don't see what that is. Does it have something to do with these endpoints being the same, yet these ones are different? I don't know. I'm gonna say that my answer here that C is incorrect. I'm pretty confident in that one. Okay, and D. Every continuous function from S to T is differentiable. Yeah, so this is correct again for the same reason. If a function from S to T is continuous, it has to be constant on each of these intervals. You know, if I draw, maybe this will be easier to see if I draw some axes here. So this is the x and this is y. So there's 1, there's 2, there's 3, there's 4. Now the function, of course, only has to be defined on these open intervals. And we don't care, like this interval is taken out. Now, the value of the function is only allowed to be 0, 1, 2, or 3. The function is not allowed to evaluate to a different number than this. So every possible function, you know, along an interval, if it's continuous, it has to be a constant. It can't just, you know, if it takes on multiple different values within one of these intervals, it would look something like this, which is not continuous. Yeah. So, you know, one particular possible function here might be something like this. And of course, this is differentiable. Now, and the derivative, of course, is going to be 0 everywhere. It's a little bit weird to be talking about a function that's differentiable when, you know, the codomain is discrete like this. Now that I think about it, do I have to worry about some kind of weird pathological thing about, you know, the topology on this set? If we think of the topology as just being inherited from the reals, then the topology on this set is just the power set. You know, it's the collection of all subsets of T. In particular, a singleton is an open set. So if I take, you know, F inverse of 1, I have to get something that's open for it to be continuous. Yeah, I'm pretty convinced here that this is these are my answers. So A and D are correct statements, and B and C are not. I'm still a little bit perplexed about option C and where the number 120 is coming from, like why that might be somewhat confusing. But I'm confident in my argument that the total number of continuous functions from S to T is exactly 164. Yeah, if I have more to say about this one, I'll write it down in the description. Thanks for watching.